Okay, so in the previous video, I introduced the potential that we're going to be dealing with, which is the finite square well. In this video, I'm going to determine the bound states by using a brute force approach. Now, this is going to be analogous to what we did with the double delta potential, where there were two ways of doing it. One was the smart way, and one is just the brute force method. Now, I'm going to do the same separation this time around. So in this video, I will do it by brute force. In the next video, I will use a trick that will make everything easier. But just to make sure that you know how to do either of those cases, I want to make sure that there is something available online for you. So that's why I'm making this video as well. So the potential that we're dealing with is this one over here, minus some amount V0, where V0 is just some positive constant, between the range minus A, and it's going to be 0 anywhere else. So that's the potential that we're going to be dealing with. And as I said, we're going to begin dealing with bound states, which basically means, as we have seen many times before, energy has to be negative. So let's now solve the Schrödinger equation for all of our regions of interest. So there's going to be first region number 1, which is right here. Then we have region number 2 here, and region number 3. Now, in the previous case where we had this double delta potential, the answer was going to be the same everywhere because the potential was 0 everywhere except at minus A and A. But in this case, region 2 will be different. So regions 1 and 3 is going to be as follows. So 1 and 3 is going to be as follows. So the Schrödinger equation will be minus h bar squared divided by 2m double derivative x squared equals e psi. Now, we have solved this already many times. So the solution here is just going to be psi equals some constant a kx plus some other constant a minus kx, and we have this for regions 1 and 3. So I'm going to call this A and B. And for region 3, now because we still have to deal with region with region 2, and I'm going to use C and D for region 2, I'm going to use here ekx and f, e to the minus kx. And as previously, we now have to discard some of these solutions because as x goes to minus infinity, this term right here is going to go to infinity, which means it's not normalizable, so we can't use it. And as x goes to infinity, this term right here will go to infinity, so it will not be normalizable. So in the end, our solutions to these two regions will be those. Now, for region number 2, what are we going to have? We are going to have minus h bar squared 2m, and just a quick reminder, k here, or k squared, is going to be 2me divided by h bar squared, and with this minus sign right here. And so in this region number 2, we have now second derivative with respect to x. And now it's very important, in this case, the potential is not 0. In this region, it's actually minus v0 psi, and this is equal to e psi. So now we isolate this second derivative as we always do. So it's going to be d squared psi dx squared. This is going to be equal to minus 2m divided by h bar squared times e plus v0 psi. Okay, so this is our equation now. So we are going to call this right here without the minus sign, because what is in here is already positive, so there's no need to include the minus sign. This is going to be L squared. Okay, so this time we have on one hand the K, which is for regions 1 and 3, and for region 2 we have this L. So this is going to be just minus L squared psi. So let's now go ahead and solve this equation. So we have d squared psi dx squared plus L squared psi equals 0. And actually we have seen equations of this form before. You can just factor it out as follows. It's going to be plus IL d dx minus IL times psi. So the solutions here will be psi in the second region will be C times e to the I Lx plus d e to the minus I Lx. This is a correct solution, but there is a better way to write this. Now, because we're going to be dealing with a potential of this form, right? This is our second region. Usually, and it's actually why we did it as well in the case for the infinite square well, it is going to be better to write this in terms of sine and cosine. Because when we apply the derivatives and all of the border conditions, the algebra will be much smoother if we have cosines and sines. Now, you could just work with the exponentials, but you will eventually have to make the transformation. So it's better to just do it right away. So how to do that? Remember that e to the I theta is going to be cosine of theta plus I sine of theta. So let's just rewrite this. So we get c times cosine of Lx plus I sine of Lx plus d cosine of Lx. Remember that cosine of minus Lx is the same as cosine of Lx because it's an even function. And then we have minus because sine is an odd function. So the minus sign that will be inside of the argument can just go outside because sine of minus x is the same as minus sine of x. So we get minus sine of Lx. There's an I here. Okay, so now we can just factor the cosine and sines. So we get cosine Lx factor of c plus d, and then we have plus sine of Lx factor of ic minus id. And now, because c and d are arbitrary constants, we can actually just rename them. So let's just say c star is going to be c plus d, so cosine Lx, and then we have that this right here is just going to be d star, just some other constant, sine of Lx, right? So we just went from the exponential form to cosine and sine, and you can actually put this solution into your differential equation, and you will see that it's also a valid solution, so everything is fine. And now, because I don't really want to have to write this star all the time, I'm just going to leave it out because c and d are just arbitrary constants. It doesn't matter, and we're not going to go back to this notation, so there's not going to be any confusion there. So this right here is now our solution for region number 2. So we have actually all of the solutions to all the 3 regions that interest us. So let me now just go ahead and put all of our solutions together. This is not supposed to be here. So this is for region 2. And regions 1 and 3 are over here. So there we go. So region number 1, region 3. Okay, so these are our solutions. Now we are going to just go here brute force method, so there's no need to begin thinking about it. That's going to be the next video. So let's just dive straight in. So I would like to just make sure to pause the video and think, what exactly are we supposed to be doing? Because I want you to know how this procedure works, and also to see the pattern between all of the different potentials that we have done before, because the procedure is actually the same. So what we have been doing for the past, I don't know, 5 or 6 videos is just applying border conditions when we have found the wave functions. So remember, the wave function have to be continuous at everywhere. So we're going to have to apply it at the borders, and the derivative is going to have to be continuous. Before, there was a discontinuity because our potential was infinite. But now, if you were to integrate the Schrödinger equation, you would find that the derivative is actually going to be continuous. There's not going to be that discontinuity. So those are the 2 conditions that we have to apply on both of our borders. So let's go for the minus a border, right? So first, continuity. That means that psi 1 of minus a has to be equal to psi 2 of minus a. So let's just write it in. It's going to be a e to the minus ka has to be equal to C cosine of LA minus D sine of LA, right? Because it's sine of minus LA, so I just take the minus sign out because it's an odd function. This is equation number 1. Now let's go for the derivative. Now the derivative here, you have to be somewhat careful because there's going to be a lot of sign changes, so please be very careful. So first, when we derive this, we get minus C times L times sine of Lx, and now we have to evaluate this at our border, which is minus a. So here we just put in minus a, but the minus sign we can actually take outside of this, so it's going to cancel out the minus that is right here. So we get plus CL sine of LA. Then we have the second part right here, which is going to be the derivative of sine is cosine, so we just get plus DL cosine of LA. The minus sign is not necessary because cosine is even, so it's the same. And then this, which is the derivative of the second part, has to be the same as the derivative of the first region. So that's going to be Ka e to the minus Ka. So this is our this is the second equation from these border conditions. I'm going to erase this so that I can fit all 4 equations in here, so that goes up. So let us now apply the conditions for the border at A. So in order to do that, there's going to be these 2 wave functions. So first, just continuity of the wave function, we get that f e to the minus Ka has to be the same as C cosine of LA plus D sine of LA, right? Our wave function has to be continuous everywhere, so we have to evaluate it at the border and they have to be equal. So that's what we did. And this is equation number 3. And then we have the continuity of the derivative. So let's derive them and make them equal when evaluated at A. So we're going to get the derivative of this is going to be minus C sine of L, and evaluated at A, it's going to be LA plus, and there's going to be an L outside, plus D, because of the chain rule, cosine of LA, and also multiplied by L. And this has to be equal to minus K f e to the minus Ka. This is equation number 4. So now we have our system of equations. These are our 4 equations that we'll have to solve now in order to determine how these quantities relate. And with that, we will be able to find a transcendental equation that tells us which energy levels are allowed. So now, just as before, as within the previous videos, we now have to find some way to connect all of these. Usually what I like to do is to see, okay, we have A e to the minus Ka here, and also here, and we also know F e to the minus Ka, and that same thing appears here. So we can actually eliminate F and A if we replace equation 1 into 2 and 3 into 4. So let's now do that. Okay, I'm going to actually draw a decent line. Okay, that's not much better, but whatever. So equation 1 into equation 3. So it's equation 2. So that's going to be K times AE minus KA, which is going to be all of this. So it's going to be KC cosine of LA minus KD sine of LA, and this has to be equal to this side right here. I flipped the sides when I was copying it, but it doesn't really matter. CL sine of LA plus DL cosine of LA. Okay, so now we have this equation right here. We have a lot of sines and cosines, and all of them depend on the same thing, which is LA. So what we could actually do is divide by cosine, for example, cosine of LA, and it's going to be look a bit better. So let's just do that and see what happens. So we're going to get kc, and this cosine is now going to be 1 because we divided by cosine. Then we have minus kd, so I'm just going to write it here just in case, 1 divided by cosine of LA. Here we're going to get sine divided by cosine, so that's just going to be the tangent of LA. This is going to be equal now to CL tangent of LA plus DL, and cosine LA is just going to be 1. So let's see, now we can just put all of our constants together. So everything with C to one side, everything with D to the other side. So let's just put C's to the left hand side, D's to the right hand side. So here we're going to get C factor of K, let's see, minus L tangent of LA, and this has to be equal to D L plus K tangent of LA. Okay, so this is going to be equation number 5. So I'm going to now get rid of what I had up here. If you need to see it, you can always just go back in the video. That way I can show everything together, and I hope that it can be a bit easier to follow. Okay, so now that we have this equation 5, let us do the same, but instead of using equations 2 and 1, let us use equations 3 and 4. So we take equation number 3 and we plug it into equation number 4. So 3 into 4. So we're going to get minus k multiplying this entire thing right here. So minus k c cosine of LA. Then we get minus k d sine of LA, and this has to be equal to what we already have on this left hand side, so it's going to be minus c sine of LA times L plus dl cosine of LA. So as we did before, we can now divide by cosine of LA, because that's going to really simplify this whole expression. And since, remember, what we are looking for, our goal, you can never forget what your goal is when solving a physics problem, right? Because otherwise, when it's a long procedure like this, you are just going to lose focus, and it's going to be really hard to know what you have to do next. So what we want to do is get to some simplified expression that depends on L and K, because we want to know what are the allowed energies of this problem, and the energy is inside L and K. So let's continue to simplify this. So it's going to be minus kc, the cosine will simplify out, minus kd tangent of LA. This has to be equal to minus cl tangent of LA plus dl, and the cosine will now simplify out. So let's, just as we did before, put c's and d's together. So c's to the left hand side, d's to the right hand side. That way it's going to be much simpler to compare this to equation 5. So when we factor out c's, we get L tangent of LA minus K, and to the right hand side we got d's, so we get D K tangent LA plus L. So now I'm going to just get rid of these intermediate steps, because I want us to just take a look at equations 5 and 6, because, well, this is equation 6, so that we can see and think about what we can do next. So we want to simplify this and find some relationship of this energy. We want to see what restraints do these values of K and L have, what does this problem tell us. So if we look at this, we can see, well, left hand side of both of these, it's K minus L tangent LA, and here we have L tangent LA minus K. So basically the second one, or equation 6, is left hand side is the same as minus the one from equation 5, and the right hand side is the same. So we can get to simplified expressions if we add or subtract these two equations. Now what should we do, add or subtract, and what is the difference going to be? Now remember, this is the brute force approach. We have not used the fact that there's any sort of even or odd solution so far. If we had done that, and we'll do that in the next video, now then we would have gotten only 2 equations here instead of 2, because that would have gotten us some of the simplified versions of this, and we are going to get 2 results here, right? Adding or subtracting. And although we will not really discuss, or at least the mathematics might not really explicitly tell us that these are the odd or even solutions, we'll see that one of those terms will be the odd solutions and one will be the even solutions. But that's just so that you can connect this with what will happen next. It's not really important to solve this right now. Okay, so let's begin by subtracting them. So let's just say 6 minus 5. So when we do that, we're going to get this right-hand side will just cancel out because it's the same, and then we are going to have 2c L tangent LA minus k, and this has to be equal to 0. So in order for this to be 0, what we want that this thing right here be 0. So L tangent of LA minus k has to be 0, or this is the same that L tangent of LA has to be equal to k. This is our first transcendental equation, and this is actually what we now want to solve in order to determine the allowed energies. L tangent LA is equal to k. Now, remember in the previous video, we got to somewhat of a similar expression where we had some exponential that depended on k, and then we have some linear function that depended on k. Now we have a function that depends on L and a function that depends on k. So we have 2 different amounts, and if we want to solve this, because there is not really an easy algebraic way to solve this, so we should go just for some sort of graphic method. So in order to graph the left and right hand side of this equation, we need to do it with respect to some variable, which before we used k, but now we have k and L. So let's just remind ourselves what these these quantities are. So k is just minus 2m e divided by h bar squared, and the square root of that, and L is just the square root of 2m e plus v0 divided by h bar squared. So we can see that both of these depend on the energy, which is something that we already knew. So let's see this thing right here. So if we want to graph this, it would be logical to think, okay, we want to just take our variable to be LA, right? Because that is what is inside of this tangent, and we're really not going to be able to change that in any meaningful way. We can't really add or multiply anything that's going to change it. So let's just say, okay, we're going to use, instead of k, some variable that also depends on the energy, and we're going to be calling it z, right, or z. So that's going to be our new variable. So the question is, how can we now transform k and L into this new variable z? Because when we have that, we're going to get just one variable that's going to be depending on the energy, and that way we are not going to have this problem of having these 2 variables. So what can we do now? Let's take a look. So, well, finding how L and z connect is going to be easy, because L is just going to be this z divided by a. Okay, so that's going to be quite simple. Now, how can we relate k to this amount? Well, in order to do that, let's now just begin looking at what we have here. So k and L are actually quite similar. So what we can actually just try is say, okay, let's add the square of these quantities. Why? Because we are at 2me inside of this and minus 2me inside of this. So actually the result of this expression is going to be quite simple. And when we have that, we can then just say, okay, but then k is going to be something related to L. So let's just take a look at that. So this is just going to be minus 2me divided by h bar squared plus 2me plus v0 divided by h bar squared. So the energy part, this will cancel out, and all we will be left with is going to be 2m v0 divided by h bar squared. So that means that we can now write this as k squared is equal to 2m v0 h bar squared minus L squared. But we know how L and Z relate, so we can just write this in terms of Z. So this is going to be 2m v0 divided by h bar squared minus, and now instead of L squared, we write Z squared divided by a squared. Okay, so this is in principle already what we are looking for, but there is a way to further simplify this, especially when we are going to be thinking about graphing it later. So let's now factor this out. So let's factor z squared divided by a squared so that we get something minus 1. So we're going to get then z squared divided by a squared factor of, and since there is none of that here, we have to multiply by the inverse of z squared divided by a squared, so that when we multiply, it cancels out and we get what we had here. So it's going to be 2m v0 a squared divided by h bar squared z squared minus 1. Okay, and now we can take the square root of this, so we get that k is just going to be the square root of all of this, but since this is squared right here, we can just take it as z a square root of 2m v0 a squared divided by h squared z squared minus 1. Now this is kind of annoying. There's a lot of constants in here, so let us define just something to get rid of it. So we can just call some constant z0 to be 2m v0 a squared divided by h bar squared, and since it's going to be divided by z squared, we might as well just call it z0 squared, right? So when we do that, we're going to get that this is just z divided by a z0 squared divided by z squared minus 1. So now this is going to be a lot easier to graph. Remember, this is just going to be the right hand side of this, so we are going to want to graph this and what we have here. So now that we know how k and L relate to z, let's plug everything into this equation right here. So we had L times tangent of LA, this is equal to k. Now I want to just pause here real quick, because remember what the problem was here, because when you see this in textbooks, they usually just say, okay, go ahead and use this substitution, but I really don't think that that is a good way to teach it, because I think it's good to just know how to determine these substitutions that you have to do, and sometimes it's really not obvious, and I thought that this was the case here, so I did want to take some time to do it, to solve it and show you the logic behind it. So, well, as I was saying, we got this L tangent LA is equal to k. We already determined that LA is going to be equal to z, and I'm kind of changing between z and z, I'm sorry about that. And L is going to be z divided by a, so it's going to be z divided by L times tangent of z. This is equal to z divided by a square root of z0 squared divided by z squared minus 1. That's actually, this is actually why we decided to factor out by this z divided by a, because now this right here will cancel out this right here. So now we get this transcendental equation, which only depends on this one variable z squared. Now there is a constant that's also going to be important, but there's only one variable, so we can actually go ahead and graph this. Well, there's not much meaning to this right here, so let's just put it like that. So we have these two functions of z, and that's going to be z. Okay, so now let's begin just graphing the tangent. Now remember, tangent is just sine divided by cosine, so this will be 0 whenever sine is 0, and sine is 0 at 0 and pi and 2 pi and 3 pi and so on and so forth. So let's say pi here and about 2 pi here and about 3 pi here. And since it is divided by cosine, then it's going to go to infinity whenever cosine goes to 0, and that happens at pi divided by 2, 3 pi divided by 2 and 5 pi divided by 2. So now we can go ahead and graph this. So the tangent is going to, as we said, go to 0 here, and it's going to be increasing. Well, I hope you're familiar with this graph. Let me just draw these lines so I can make somewhat of a better job at sketching this. I'm not really good at sketching. Then we have 2 pi. Let's see, it goes to infinity here, then also here, and so on. So we're going to have all of these lines from the tangent, and the negative part is not interesting because this root will never be negative, so there's not much point in paying any attention to that. And now I'm going to use a different color for the square root. So the square root is just going to be decaying. And now in order to draw it exactly, you need to know z0, because the square root is going to, this kind of looks like a straight line, but I promise it's a square root. So this is going to be going to 0, and it's going to be 0 whenever this thing right here is 0. So it's going to be 0 when z is equal to z0. Okay, so actually, and remember, what are we doing here? We are graphing these allowed energies, because the energy is inside of this expression z. So whenever these two functions encounter each other, that is going to be the point where the are allowed bound states. So the energies are going to be defined by where these two functions meet. So that depends on z0, and remember z0 is, let's see here, it depends on the strength of the potential and also of how wide this potential is. Okay, so depending on how wide and how strong it is, it's going to have more and more bound states. And in fact, you can see as v0 and a grow larger and larger, z0 is going to grow larger and larger. And what does that mean? That means that the point where this is going to go to 0 is going to be every time larger. That means there's going to be more and more intersections, and that means more and more allowed bound states. And in fact, as the, let's see, where was it? Yes, as our z0 grows larger and larger and tends to infinity, which is going to be what happens if our potential is going to go to infinity, then our allowed energy states are actually going to go to be what we saw in the case of the infinite square well. And you can actually, that's actually a solution that you can find if this goes to infinity, and you will do this graphically. Now, as I said in the previous video, solving this numerically requires you to have some value for v0, some value for this a. So we can't really go any further than this if we don't have any actual value to work with. And this is actually usually what is good enough for answers, because now you can know how many bound states there are. And the answer is, of course, it depends on the strength of the potential and its width. So now we saw this first case. Let us now go to the case where we add these two equations, so 5 plus 6. So in that case, let's see, the left side is going to cancel out, so we're going to get 2 times d times L plus K tangent of LA. Yes, I'm missing one parenthesis. This is going to be equal to 0. So this means that L plus K tangent of LA have to be equal to 0. So here we can use the same substitution that we used before. So let's just write this as L is equal to minus K tangent of LA. So let's say Z is going to be LA. And in fact, maybe to make it even more obvious, let's just divide by the tangent, which is to say multiply by the cotangent. So we get L cotangent of LA is going to be equal to minus K. And this is basically the same thing that we had before, except with cotangent instead of tangent and with a minus sign right here. So what this is going to be, let's just use Z is equal to LA, which means that L is equal to Z divided by A, and K, as before, is going to be Z divided by A. times square root of z0 squared, z squared minus 1. Okay, so this is going to be then z divided by a, cotangent of LA. This is going to be then equal to minus z divided by a, square root of z0 squared, z squared minus 1. So we can now cancel out, whoops, not the minus sign, but everything else. So, and cotangent of LA is supposed to be cotangent of z. So now we have this transcendental equation, which is actually quite similar to the one we had before, but with the cotangent instead of the tangent. So, and actually let us put the minus sign to the left-hand side in order for it to be somewhat easier to graph. Let's see, I'm going to select it like this. There we go. So just as before, we need to solve this using graphical methods because it's really not easy at all to determine the solution otherwise. So let's just make a graph. Oops, that's not a straight line. In which we're going to graph these functions of z in terms of z. Remember, this z is what contains the energy. So this is going to be 0. And now, well, let's begin by graphing the cotangent. So the cotangent is going to be 0 because it's cosine divided by sine. It's going to be 0 whenever cosine is 0, which is going to be at pi over 2 and 3 pi over 2 and 5 pi over 2 and so on. And it's going to go to infinity whenever sine goes to 0, which is at pi and 2 pi and 3 pi and so on. So, and because it has a minus sign, it's actually going to be flipped from what it usually is. So its graph will just go somewhat like this. I'm going to ignore the negative parts as I did before, because it's just not going to be relevant here because our square root will never go to negative. So it doesn't really matter. There's no reason to include it. So the graph will just be somewhat like that. Obviously, this is just a quick sketch, so it's by no means very accurate. It's not an accurate depiction, but you get the general sense. And when we graph the square root, it's just going to be some decaying function. So there's actually, well, and it goes to 0 at some point, as before, at the point z0. So now there is a big difference here between this and what we saw in the previous case, because in the previous case, there was always going to be some intersection between this tangent function and this square root, because there is this tangent that began at 0. So there was no way that this was going to fall off before touching it, but that's not the case here. If the z0 is not big enough, this function might just go down somewhat like this, and it would just not touch any of these cotangent lines, which means that there is not going to be an allowed bound state for this case. Now, we don't really know what the interpretation of this case is just yet, but as we'll see in the next video, these are actually the odd states. So there will not always be odd states if the potential is not strong enough. Not only the potential, if this z0 is not big enough, because remember, z0 also depends on the width of this well. So now you could determine the exact values where these intersections occur if you had numerical values for a and for v0, but in that case we just have to plug it in and use a graphical method or numerical method to determine where they intersect. But that is really not what we're interested in here. We determined how many of these points there are. In fact, if you know that z0, for example, is let's say 3 pi, then it would fall off around here. So you would know, okay, there are 3 odd states, and also if it's 3 pi, there are also going to be 3 even states. So it's going to be 6 states in total, so 6 bound states. So that would actually give you already a lot of information without having to do any explicit calculations. That's why using these graphical methods is so powerful. You can get a lot of information without really having to do many calculations. So that is it for this video. What we did here, just as a quick recap, we had this bound state, and all we had to do is solve the Schrödinger equation for each of the regions, which is the same that we are always doing. And once we had our wave functions, we had to apply the border conditions, all 4 of them, and we then had to solve this system of equations, to which we found 2 of these transcendental equations, which we had to solve in a graphical method, because, well, it's really not easy at all to solve just like that. So that's what we did here. So I hope that you found this useful. If you did, make sure to leave a comment and subscribe. That's really helpful to me. So I will see you in the next video, where we're going to do the same thing, but this time using a very good trick that we have already used before, the trick that the potential is even. So that's going to make everything a lot easier. So I will see you then. Tengo un calor, loco. No, I need to film more first. I'm gonna film more later. Tucci.